Welcome to this explainer. Okay, picture this. Have you ever stared at a glaring red compiler error in your Java IDE and just thought, come on, this math makes perfect sense, why won't it compile? Well, trust me, you are definitely not alone. Today, we're going to act as your technical mentors and pull back the curtain on exactly how Java handles memory behind the scenes. We're going to completely demystify Java type conversions and promotions. Understanding these invisible, underlying rules will literally save you from hours of frustrating debugging and honestly give you total control over how your data actually behaves.
Okay, let's dive right into this roadmap. We're looking at an introduction to data types, implicit widening conversions, explicit narrowing and casting, how characters, decimals, and booleans fit in, the truncation effect, and finally, automatic type promotions. So get your mental scaffolding ready.
All right, starting with Section 1. Introduction to data types as containers of memory.
To really grasp how Java moves data around, we need to completely shift how we visualize variables. Stop thinking of them just as abstract numbers, and start thinking of them as physical containers of distinct bit sizes. For example, think of an 8-bit byte as a small coffee cup. It can only safely hold values from -128 to +127. Now compare that to a 32-bit int. That's like a massive industrial bucket capable of holding billions. The primary conflict in Java always pops up when we attempt to pour the contents of one memory container into another of a completely different size.
Moving on to Section 2. Implicit widening conversions. Automatic conversion.
This right here is the first rule of conversions. It focuses on scenarios where Java quietly handles all the heavy lifting for you. Just look at this fundamental duality. On the left, we've got implicit, or widening conversions. If you have a value in a byte, say the number 24, and you assign it to an int variable, Java just automatically does it for you. Why? Well, because you're pouring a small cup of water into a massive bucket. There is absolutely zero risk of data spilling. But on the right side, we have explicit, or narrowing conversions, and these require your manual permission.
Which brings us to Section 3, explicit narrowing and casting, manual typecasting. This is the exact opposite scenario, and frankly, a much more dangerous one, where the destination container is actually smaller than the source container. The main takeaway is that Java will not automatically spill your data. You must explicitly use casting to take responsibility. If you declare an integer with a value of 300 and then try to cram that 32-bit bucket into an 8-bit byte cup, the compiler instantly throws an error. To force it, you have to write the word byte in parentheses right before the variable. This is called casting. You are essentially signing a waiver telling the Java compiler, hey, I know what I'm doing, please force this data in.
Section 4. Characters, decimals, and booleans as special data types.
Now that we have the basic cup and bucket analogy down with integers, we need to see how these rules apply to other common data types. Take the number 97. If you create a char variable and assign it the lowercase letter a, Java internally stores it in memory as its Unicode integer value, which is 97. And since a character in Java is 16 bits, if you try to assign that character to a 32-bit integer bucket, it effortlessly widens. It'll output 97 without you needing to do any casting whatsoever.
But what about decimals and true or false values? Well, if you explicitly cast a 32-bit float down to a 32-bit int, Java performs what's known as a truncating conversion. It completely chops off the decimal. So 16.678 just becomes 16. It doesn't round up, it simply lops the end off. And then there are booleans. Listen closely to this one, because Java isn't going to let you play fast and loose here. Booleans are a strictly isolated data type. Because true and false are not stored as numbers, they cannot be converted, widened, or cast to any other data type, ever. Doing so results in an immediate syntax error.
All right, Section 5, the truncation effect, the math of data loss.
Now, what's really interesting here is the underlying math of data loss. What actually happens when you sign that developer waiver and cast a huge integer into a tiny byte? Let's walk through the exact under-the-hood binary truncation process. Imagine you force the integer 300 into a tiny byte container. Step 1. Java converts 300 into a 32-bit binary number. Step 2. Because a byte can only hold 8 bits, Java literally takes a chainsaw to the binary code and chops off the top 24 bits. Step 3. It converts those remaining 8 bits back to decimal. A super handy mathematical shortcut for this is taking your large number and finding the modulo of the destination's range. Since an 8-bit byte has 256 possible combinations, you calculate 300 modulo 256. And the remainder is 44.
Tragically, your massive value of 300 shrinks all the way down to 44. This vividly cements exactly why explicit narrowing conversions require extreme caution. You aren't just squishing the number down, you are literally lobotomizing its binary code. If you aren't perfectly aware of the math, your program will start spitting out wildly incorrect data.
Finally, Section 6. Automatic type promotions during mathematical operations.
We're now transitioning into the final and frankly most frequent source of confusion in technical interviews, what happens dynamically during mathematical equations. I want you to pose this mystery to yourself. You declare byte b equals 50. In the very next line, you write b equals b times 2. Now, 50 times 2 is 100. The maximum limit for a byte is 127. So 100 clearly fits within the byte limit, right? Yet this instantly causes a compiler error. Why does a calculation that fits perfectly within the container fail?
So the crucial point is that Java acts as a smart calculator. During mathematical operations, Java looks at variables like bytes and shorts and thinks, if I multiply these, the intermediate answer might actually exceed 127 and crash the program. So to protect you from intermediate overflows, Java temporarily auto-promotes those smaller containers into 32-bit integers before it even does the math. So b times 2 is actually evaluated as an int. When you try to save that int back into the byte b variable, it triggers the narrowing rule we learned earlier. You're trying to put an int into a byte. To fix it, you have to explicitly cast the entire mathematical result back into a byte.
And this brilliantly illustrates the exact promotion hierarchy Java uses. If an equation includes a byte, short, or char, the whole thing is automatically evaluated as an int. But it scales up from there. If you have an equation with a long, the entire mathematical expression becomes a long. If there's a float anywhere in there, the result is a float. And if there's a double, the absolute largest primitive data type, the entire result becomes a double.
To put it simply, when combining different variables, Java continually promotes the expression to the largest available container present in the equation. If you multiply a float by a byte, add it to an int, divide it by a char, and subtract a double, Java takes one look at that double, sees it's the biggest bucket in the room, and upgrades the final result to a double. It guarantees that no matter how complex the math gets, the container is always large enough to hold the final answer without overflowing.
Think back to your own code for a second. We've seen how a seemingly harmless conversion can turn the number 300 into 44, or how a simple multiplication can completely break a build. Could a misunderstanding of container sizes and implicit rules be the hidden reason behind your app's weirdest calculation bugs? Knowing exactly how your data is promoted, truncated, and stored is the difference between writing code that just barely works and writing code that is truly bulletproof. Take a really close look at your math equations the next time you boot up your IDE. Thanks for joining me on this explainer, and happy coding!